better at it than I am.
Can we like turn off a light, like a backlight or something? Because there's that glare on there all the time.
Sure.
That you're up. Somebody. We're looking back like someone's gonna do it.
That's my mom and dad and say, hey, you like bro?
Yep, it is.
Do something about it. All right, let's jump into this. Oh, suitcase. I need a light. There we go. All right, so what we're going to do today is this really sets the tone for orthographic projection, and you've been doing some of these rules all the way along, but as we come outside the glass box, we need a couple others to handle our auxiliary views. And so these all apply for multi-view drawings and our auxiliary views. And let's go through the proofs of these. Now, I've stated before that you don't have to visualize anything to be able to draw it effectively, and you don't. But it certainly helps if you can. That's why we spend a lot of time on trying to visualize and doing models and things of that nature. But keep in mind your 8 rules of orthographic projection and then D's for perspective geometry will draw pretty much anything on the planet if you know them. All right, so let's go through them. I'm going to start on page 698 under the bio of Gaspar Monge. And we have some italicized text at the bottom, geometric rule 1. And I want to go through these in detail so that we can see them, because in essence they progress from lines to planes and different rotations that we'll do. So the true length line. If a line is positioned parallel to a projection plane and the line of sight is perpendicular to that projection plane, the line appears true length. In essence, that says the same thing as our rule 1. The line appears true length in the viewing plane parallel to it. Now they're using line of sight versus projection plane. That's the only difference in the two definitions, but keep in mind your line of sight in orthographic projection is always perpendicular to your projection plane. So therefore both statements really read true. Let's look at some examples. The first example would be in 1413. So let's go there. And in essence, it's this figure. Let me kind of zoom in on it. Right here. Now in here, as you look through these, you're going to see 2 things as you go through this chapter. This is a great chapter for backup material on what we've been doing. You're going to see 2 methods the author uses to produce these. There's the auxiliary view method and the revolution method. Both are valid methods. Okay, I am not going to go to the revolution method because we already know the auxiliary view method. So as you go through the text, if you see auxiliary view, that's using fold lines and projection just like we've done all the way along. There is another geometric method out there called the revolution method, or if I'm saying that right, revolution, not revolutionary. It's a revolution method. I don't know why we need to know 2. And I don't know that we want to take the time to do another week of study to know the other way to get the exact same answer. So we're sticking with the auxiliary view method as you go through chapter 14. So in essence, what that states, here's my fold line. I have a line that is parallel to that fold line. Remember, for me to project into this view, I am looking perpendicular to that fold line, right? Because this represents the edge of the glass box. Therefore, the line up here must project true length. So it's the first step in the process is determining which lines are true length. There's a little better example on 1417 where they actually unfold the box for you right here and show you this process. So in this view, they've taken your 3 principal views, front, top, right. You see the line drawn in the right and the top. Notice that in here, again, it is parallel to the projection plane, therefore the front view must be true length. Conversely, if it's true length in the front view, then it's got to be parallel on the right side view also, doesn't it? Just kind of common sense on that. Any questions on projecting a true length line and how we go about getting it? The author does give you a great example on figure 1418. and there's text that goes through this. Okay? So let's just kind of walk through these steps real quick. In essence, what he's doing here is projecting a true length line. So you got a given situation, which is shown right here. Now they've gotten rid of, keep in mind, this is a plane, but they've broken it to just a line for this example. But in real life, that line's attached to a plane somewhere, right? So in essence, here's our given situation. We look at it here. Okay? We've got to analyze it. Is this line parallel to that viewing plane? No. No. So therefore, that is not true length. Is this line parallel to that viewing plane? No, it's not. Therefore, that is not true length. Now, how am I looking at that? I don't know. Am I looking at it this way or this way? And I'll tell you, I've spent a lot of time with pencils trying to visualize exactly how that thing works, and it gets pretty tough. And so, in essence, I kind of quit doing that over time, and I trust my laws because they've never let me down. Okay? And I just run with those. So in essence, what the author then does is he says, okay, we need to project it. So what he's doing is he's coming in and drawing a viewing plane parallel to either of these two lines. Doesn't matter which one you go next to it as you come through the progress, because this line doesn't change from view to view, does it? No, our view of the line changes, but the line doesn't change. So therefore, if we drew a viewing plane parallel to any of them and projected, we should get the exact same answer off of any view. The author just chose this bottom one here. So he comes in here, projecting perpendicular, right? Just like we did yesterday. Here's where you get your missing dimension. Let's see. Let me go down to the next step. Okay. Try and get all these here in the same view. There we go. So as the author projects it, we know we can project perpendicular to a viewing plane. We know point G falls on that line, L on that line, we just don't know where. So we go back to the rear view, they're measuring from fold line to point, and they're laying that off in these two views. So there's point G, there's point L, connect the dots, has to be true length. You did for an example, you could grab this thing and pull it off the other line, project both of them, they should be both true length. Measure them, see if you get the exact same answer. That'd be a good little test to see that this works. All right, so can you project a true length line? Yes. Okay. All right, so the next step from that is then applying it to a point view. So we've got law 2. We put on ours, where I've tried to set this down, the true length line appears as a point in the viewing plane perpendicular to it. Okay, this is in the text. The author actually uses a couple rules for this one. So let's read the text first. Go to 702. So here's the text, the italicized on the right-hand column. Rule 2, point view of a line. If a line of sight is parallel to a true length line, the line will appear as a point view in the adjacent view. And then you have a corollary meaning from that. Any adjacent view of a point view of a line will show the true length of the line. So what we're in essence looking for here is point view. Let's go to figure 14. It's on page 697. This view shows the process of where we would build off of law 1. Remember, again, we're trying to attach these to planes in the real world. So in essence, here's our two lines we're given. We notice that neither one of these lines are parallel to that viewing plane, therefore they're both foreshortened views of that line. We need to project true length. So in essence, we come, draw it parallel, project it. So when I go point to here, that same distance is here. This distance, same as that distance. Now, once I have that, and I know I have a true length line, now I can get point view. Now remember, point view, what does that really mean in relationship to a plane? Corner, or I may be looking at a corner, I may be looking at one of many corners. edge. Edge. Okay? That's what you're looking for here, folks. That's what Rule 2 is all about. And it doesn't say edge in it. All it says is get the point view of a line. Well, a line bounds a plane. You look at any one of the edges of a plane as a point, you will see that plane on edge. You will. Okay? Guaranteed. That's in essence what we're trying to do. They're showing point line here. So in essence, they projected straight through. Okay, that's law 1. Then they went from fold line to point. Now, since this one's parallel, okay, remember this was coming to find our true length line. This distance and this distance the same. Therefore, we set that off, and that's the 2 points. How do you know which point's in front and which point's behind? So would you be looking at it like that or like that? Okay. How do you know which point is in front? They say G's in front, L's behind. We list the front one first. Well, the closest point to this viewing plane line, or this fold line, will always be the one in front. So G's closer, it's going to be there because the rotation angle is 90 degrees like that. Okay? So that's how you always know which one's in front. This point will always be in front of this if I project this way. If I came this way, L would be in front. Okay? In essence, we now have point view. Now, as far as planes go in the projection of stuff, this is necessary for oblique planes. It's also necessary for dihedral angles. They do have a good example in here on dihedrals besides what we saw on 13. I didn't write this page number down, but I do want to show you that. It's on page 707. So if we're looking for dihedral angles, we apply laws 1 and 2, and that's all we need. This is the example of it. So here you have 2 views. Okay. Again, you just look at it and say, okay, that's not true length, that's not true length. None of these are true length. They're all foreshortened because nothing's parallel to here. When I look at this view, nothing's parallel to there, therefore everything up here is foreshortened. Now, what we've really done here, folks, is we've progressed from 2 points into lines, right? Now to planes. Well, when you do dihedrals, what you want to focus on is that line right there, or that line right there. It's the line of intersection between the 2 planes. Because that line is common to both planes, correct? That's why we focus on that line. And then we just carry the rest of them with it. So they came in and they drew a viewing plane parallel to my line of intersection between the 2 planes. They projected both planes into this view, but all we care about really is that one. We now know that line is true length. Then we can apply law 2, which states that we're going to go perpendicular to our true length line. I see that line as a point right there. That line is on both planes, therefore I see both planes as an edge. I see the full angle of the cut, true size. Okay, so this is how you would apply it in the process of solving a dihedral angle problem. For the meats and bones of how you make the projection, that is given back, I wrote this one down, this is figure 1422. It's this little example right here below where we talked about those instances. Okay. Where again, here's your given. They projected for true length, and then they projected for point view right here. And then the text goes through how you get all of those measurements. Any questions on that one? Okay. In essence, do you see a kind of a reoccurring theme as you project these? That we always do the same thing, we just kind of keep rotating an object? And I think you will as we go through these if you haven't seen it yet. Let's look at 3. The author actually has 3 laws on this. None of them really state what ours does, but you can make that assumption. Let's go to 705. In essence, rule 3 here, which is not on your rules, states that planar surfaces of any shape appear either as edges or as surfaces of similar configuration. Remember the rules of orthographic projection? This was rule 7. That a plane always appears as a plane, has the same number of sides, appears similar unless you see it on edge. And then we see it as an edge. And that's pretty straightforward, right? A plane doesn't change, just our view of the plane changes. So this really is not what I consider one of ours. We know that already. Next one, edge view of a plane. If the line in a plane appears as a point, the plane appears as an edge. That's the same thing as number 2, right? So I'm just skipping over those two. Go down to the bottom of 705. Here's rule 5. A true size plane must be perpendicular to the line of sight and must appear as an edge in all adjacent views. In essence, isn't that the definition of a normal plane? What is the definition of a normal plane? Appears true size and shape in one view as an edge in all adjacents. All this is stating, you can get to true size and shape in any plane. All adjacents must be edge views. And we know that because we're going to turn law 1 to find true length, law 2 to get edge view, law 3 to get true size and shape. In essence, we're following this. Hence, ours, which has kind of been taken all these and put together, a plane appears true size and shape in the viewing plane parallel to its edge view. So put all 3 of these together. We'll come look at something here in a minute. Got to find true length, got to find point, get your true size. This will solve all problems geometric. The best example on this one, there's a couple of good examples in this chapter, but they have a shortcut into it, and I'm not going to bring that in until tomorrow. So let's go back to 13 and look at this one, figure 13, 18. It's this guy right here on page 669. In essence here, we've got an oblique plane. They solve true length because it's given. Again, we went through this yesterday. This line's parallel to that viewing plane, therefore it must be true length in this view. There's law 1, satisfied. We didn't have to project for it. If you didn't have a true length line, you've got to project for it. Okay, just grab any of these 3 lines on this plane, and you can rotate to get true length. In this case, it's given to us. They then applied law 2. We went perpendicular true length line. That gave us point view of that line, which gives us edge of the entire plane. Then we go parallel, or law 3, parallel to our edge view gives us true length. Okay. True size, I guess, because we're now talking about planes. Okay. So all sides are true length. In essence, that's it, folks. If you can do those things, you can basically take these 3 complicated planes, inclines, dihedrals, obliques, and project them true length. And you can get them right the very first time you do them. Okay. Now keep in mind as you go through here, once you identify your plane and you know it's inclined, then you should know immediately if it's inclined, you've already done law 2. You need to apply law 3 only. Because remember that when we looked at inclines. Let me just go to one on this chapter, just so we can make sure we summarize this correctly. Let me just go take one here. Let's look at this one. So here's an inclined plane. Foreshorten, edge, foreshorten. Definition of inclined. Now, I'm looking at this one with this side true length, but does it matter if it's true length? No, doesn't matter a bit. Because really, what's the point of doing law 1 and 2? It's to get to edge view. An inclined plane, by definition, has an edge in one of our orthographic views. You're already at law 2. I don't care if there's anything true length on it or not. All I need is edge. Then I'm going to apply law 3. View fold line, parallel to it, must project true size. That's why when I say whenever you're at an inclined plane and you see an edge view, you don't have to do laws 1 and 2. You just do law 3 because you're already at the edge. If you have a dihedral, you need to apply law 1 and 2 because we want to get to the edge view. Keep in mind that you are always looking at the line of intersection on those two planes. And that will find the result of a dihedral. If you go with an oblique, or you recognize this one, you need to apply laws 1, 2, and 3. All 3 laws. Many times with the dihedral and the oblique, law 1's already going to be given to you because standard orthographic projection might already have it. But that's up to you to determine by doing your multi-views and then analyzing the figure. Any questions on these? I think if you know that, folks, you identify the planes, the hard part, and then it's just reapplying the same principles time and time again to get it rotated to the view that gives us our answers. This is pretty powerful mathematics. I mean, to do this in an analytical sense, besides using geometry, would fill up pages of calculations. I mean, seriously, I could sit down and I could run 5, 6 calculations. I could come up with this answer using planar trigonometry and calculus and all that, but boy, I think that's only going to get paid for on a university campus. We're not paying anybody in the work world to do that. We need faster, more accurate solutions than that, and this gives it to us. By the way, you know how many times I used calculus on the job? 1 time, and I didn't have to do it that 1 time because it takes too much time, and time is money. We now have computer programs that do it. You know, structural engineers really don't crunch numbers anymore. We put it into a CAD package and it spits out our answers. We still have to know the stuff in the background, but we don't do the math on the job site. It takes too long. All right, so there's your 3. I've got something for a little practice on this. Although if you get a ball of twine, it's not to chase some trucks. All right, so let's look at what I want you to do with these. This is really trying, I'm going to give you I think there's 11 or 12 of these worksheets over the course of the next 2-3 days. And they're all about making this jump from points to lines to planes and getting this technique down. So in essence, let's just look at it. I do not want this turned in, by the way. I would like you to do it today, and we will go over it as a class tomorrow. So the best way to do these, I would get a set of dividers and some type of triangle or straight edge. So let's just go through what we're doing on these worksheets. So the first one, we're in essence going to project points. And this is all about just making sure you can use the fold line method to project points. So in essence, all you're doing is locating the point. In each of the following problems, locate the points in the view of which it is missing. Label all points. Folks, I think you should do this. Okay, like I said, I'm not going to grade this one. We'll go over it as a class. But here's what I would, just so you make the connection. This is point 1. That's point 1. Same 2 points, given in a front and right view. How do I project it? Well, I get my triangle. I can project perpendicular, right? I know point 1 falls on this line. I just don't know where. Okay, now we pretty much always use a meter line to transfer this, right? Use the fold line, folks, because it's going to pay dividends for you here in a couple of worksheets. So I'll just come in with a divider, and I want to measure the distance from fold line to point, like here, and then I'll transfer that up to this view. So there is point 1. Any questions on what we did?
Yeah, you repeat that one.
Sure. So I'm trying to locate it in the top view. I can always project perpendicular in between views, right? Okay, so I throw that line up. I know point 1 has to fall on the line, I just don't know where. So I go to a related view here, and I measure the distance from fold line to point. So the distance you're measuring is this distance right here. That distance is the same as this distance from fold line to point. There you good, Amy? Anybody else? Okay. I think the rest of those follow that same atmosphere. Let's go to sheet 2.